What specific problem does conditional activation steering, CAST, aim to solve in the context of activation steering methods?
Conditional Activation Steering, CAST, aims to solve the problem of lack of conditional control in existing activation steering methods, which indiscriminately apply modifications across all inputs regardless of context. Current activation steering techniques, while effective in altering model behavior, do not allow for selective refusal of harmful prompts while still enabling responses to harmless ones. CAST introduces a new type of steering vector, the condition vector, which captures specific activation patterns induced by prompts, allowing for context-dependent control over LLM behaviors. This method enables the model to apply a refusal vector only when certain conditions are met, thus enhancing the model's utility by allowing it to refuse harmful content selectively. Overall, CAST improves the controllability of LLMs without incurring significant costs in data, runtime, or computational efficiency.
Please illustrate step-by-step how conditional activation steering works, detailing the role and extraction process of both the condition vector and behavior vector.
Conditional Activation Steering, CAST, operates through a systematic process that involves the extraction and application of two key components, the condition vector and the behavior vector. 1. Extraction of vectors. The process begins by gathering contrasting examples that exemplify the presence and absence of a target behavior or condition. For the behavior vector, the average hidden states of positive examples, those exhibiting the desired behavior, and negative examples, those not exhibiting it, are computed at a specific layer. This is followed by mean-centering these hidden states and applying principal component analysis, PCA, to extract the first principal component, which becomes the behavior vector. For the condition vector, a similar approach is taken, but the average hidden states are computed for all tokens of each example to capture a holistic representation, and PCA is again used to extract the first principal component. 2. Condition checking. During inference, the model's hidden state is compared to the condition vector using cosine similarity to determine if the condition is met. A thresholding function is applied to this similarity score to decide whether to activate the behavior vector. If the similarity score is below the threshold, the behavior vector is added to the model's hidden states, effectively altering its behavior. 3. Behavior modification. The behavior vector, which is designed to induce specific behaviors, like refusal, is added to the model's activations at chosen layers during the forward pass. The scaling factor determines the strength of this addition, allowing for controlled modification of the model's responses based on the context provided by the condition vector. 4. Multi-conditioning. CAST allows for the logical composition of multiple condition vectors, enabling the model to respond selectively to various harmful prompts while maintaining compliance with benign ones. This is achieved by creating rules that combine different conditions, enhancing the model's ability to navigate complex scenarios. 5. Implementation and efficiency. The entire process is efficient as it does not require weight updates to the model. Instead, it leverages the model's existing representations, allowing for rapid implementation of conditional behaviors with minimal computational overhead.
Can you provide a concrete example demonstrating the application of CAST in a scenario where a model must refuse harmful prompts while still responding to harmless ones?
A concrete example of applying conditional activation steering, CAST, involves conditioning a language model to refuse harmful prompts related to hate speech while still allowing it to respond to harmless inquiries. In the experimental setup, the researchers generated 4,050 harmful prompts across various categories, including hate speech, and paired them with benign instructions from the alpaca dataset. By extracting a harmful condition vector from these prompts, the model was able to selectively increase refusal rates for harmful content while maintaining compliance with harmless prompts. The results demonstrated that, unlike traditional activation steering methods that indiscriminately increased refusal rates across all inputs, CAST effectively allowed the model to differentiate between harmful and harmless prompts, thereby enhancing its utility in real-world applications. This selective refusal mechanism illustrates the practical benefits of CAST in ensuring responsible AI behavior.
What experimental metrics or benchmarks were used to validate the effectiveness of CAST, and what were the main findings regarding its performance compared to traditional activation steering methods?
The effectiveness of conditional activation steering, CAST, was validated through experiments that involved testing on unseen datasets, specifically 500 harmless prompts from the Alpaca dataset and 450 harmful prompts from the Sorry Bench dataset. The main findings indicated that CAST selectively increased refusal rates for harmful content while maintaining low refusal rates for harmless prompts, contrasting with traditional activation steering methods that indiscriminately raised refusal rates across all inputs. Additionally, the experiments demonstrated that CAST could implement more nuanced behavioral rules, such as refusing specific categories of harmful content, which traditional methods struggled to achieve. The results showed that conditioning the behavior vector on the condition vector allowed for a systematic and flexible approach to model behavior, enhancing the model's utility in real-world applications. Overall, CAST exhibited superior performance in selectively steering model responses compared to the uniform application of traditional activation steering techniques.
What limitations of conditional activation steering are acknowledged in the paper, and how might these affect its applicability in real-world scenarios?
The paper acknowledges several limitations of conditional activation steering, CAST. Firstly, while CAST allows for selective refusal of harmful prompts, it may not fully address the variability in harmful content across different contexts, which complicates the creation of universal harm models. Additionally, the method exhibits a saturation effect, where performance stabilizes after a certain point, indicating that its effectiveness is more dependent on the model's inherent capacity rather than the volume of conditioning data. Furthermore, the paper notes that the duality property of conditioning can lead to conflicts when multiple refusal conditions are applied simultaneously, potentially reducing the effectiveness of the induced refusal behaviors. These limitations suggest that while CAST enhances control over model behavior, its real-world applicability may be constrained by the complexity of context-dependent harmfulness and the potential for conflicting conditions.
What future research directions do the authors suggest based on their findings, particularly concerning the scalability and adaptability of CAST for other tasks or model architectures?
The authors suggest several future research directions based on their findings with conditional activation steering, CAST. They highlight the potential for further exploration of multi-conditioning, which could enhance the model's ability to handle more complex refusal behaviors by logically combining multiple condition vectors. Additionally, they indicate that the scalability of CAST could be examined by applying it to different model architectures beyond those tested, assessing its adaptability across various language models. The authors also note the importance of refining the thresholding functions used in CAST to improve the sensitivity and specificity of the model's responses to harmful prompts. Lastly, they propose investigating the effectiveness of CAST in unseen categories, which could provide insights into its generalizability and robustness in real-world applications.